Welcome to Engineering Simplified. How does a motor spin without anything ever physically touching the rotating part inside it? No brushes, no sliding contacts, nothing wearing against anything else. Just a shaft that spins for years on end. The answer is one of the most elegant ideas in electrical engineering, and by the end of this video, you'll understand exactly how a three-phase AC induction motor pulls it off. Let's get into it. To understand an induction motor, we first need to understand the supply feeding it. Three-phase power is made up of three separate AC voltages, each identical in shape and frequency, but offset from each other by 120 electrical degrees. Inside the motor's outer casing, called the stator, there are three sets of windings, physically arranged 120 degrees apart around the inside of the frame. Each winding is connected to one of those three phases. Here's where it gets interesting. Because each winding is fed a voltage that peaks at a different moment in time, and because the windings are positioned at different points around the stator, the combined magnetic field doesn't sit still. As each phase rises and falls in turn, the magnetic field's peak effectively sweeps around the inside of the stator once every electrical cycle. This is called the rotating magnetic field, and it's the entire foundation the motor is built on. The speed of that rotating field is called synchronous speed, and it depends on just two things: the supply frequency and how many magnetic poles the winding is arranged into. The formula is synchronous speed equals 120 times frequency divided by the number of poles. On a standard 50 Hz supply with a simple two-pole winding, that rotating field sweeps around at 3,000 revolutions per minute. Add more poles, and the field rotates proportionally slower, which is exactly how manufacturers offer motors at different standard speeds without ever changing the supply frequency itself. Now here's the part that gives this motor its name. Sitting inside the stator is the rotor, and in the most common design, the squirrel cage rotor, it's just a cylindrical core with conducting bars running along its length. Those bars are short-circuited together at each end by conducting rings. Critically, the rotor has no external electrical connection whatsoever. No slip rings, no brushes, no wires running to it at all. If you're enjoying this, like, comment and subscribe. And check out the other Engineering Simplified playlists. So how does a rotor with no electrical connection produce any torque at all? This is where electromagnetic induction takes over, the same principle Michael Faraday discovered nearly 2 centuries ago. As the rotating magnetic field sweeps past the stationary bars of the rotor, it induces a voltage in them, exactly like a transformer induces voltage in a secondary winding. Since the bars are short-circuited, that voltage immediately drives a current through them. By Lenz's law, any induced current always opposes the change that created it. So the current in the rotor bars generates its own magnetic field, which interacts with the stator's rotating field. That interaction drags the rotor around, chasing after the rotating field, trying to catch up to it. That dragging force is torque, produced entirely through induction. No direct electrical connection needed anywhere on the rotor. But here's the crucial detail that trips people up. The rotor can never actually catch up to the rotating field. If it ever spun at exactly synchronous speed, there'd be no relative motion between the rotor bars and the field. No relative motion means no induced voltage, no induced current, and therefore no torque at all. The motor would simply coast and slow back down. So the rotor always spins slightly slower than the rotating field, and that difference is called slip. Slip is usually expressed as a percentage, comparing synchronous speed to actual rotor speed. Under no load, slip might be less than 1%, since only a tiny speed difference is needed to overcome friction. Under full mechanical load, slip typically increases to around 2 to 5% for most industrial motors, since more current and more relative motion is needed to produce the extra torque the load demands. This self-adjusting relationship is a major reason induction motors are so widely used. The motor automatically produces more torque as load increases without any external control system telling it to. The common mistake people make is assuming an induction motor runs at exactly the neat speed from the synchronous formula, 3,000, 1,500, or 1,000 revolutions per minute. In reality, the nameplate already accounts for slip under rated load. That's why you'll often see oddly specific numbers like 2,880 or 1,450 revolutions per minute instead. That gap isn't a manufacturing quirk, it's slip, and it's fundamental to how the motor generates torque in the first place. So remember, a three-phase supply creates a rotating magnetic field in the stator. That field induces current in the unconnected rotor bars purely through electromagnetic induction, and the interaction between the two fields drags the rotor around. It spins at a speed just slightly below synchronous, never quite catching up, because catching up would stop the very induction that makes it spin in the first place. Drop a like, comment the topic you'd like to see explained next, and subscribe. It genuinely helps this channel grow. See you in the next Engineering Simplified video.